All right, so in this video we're going to do some example problems about the buoyant force or Archimedes principle. So to start, let's remember some of the relationships which are important. First, we have the apparent weight of an object that's placed inside of a fluid. So for instance, if you have a 10-pound dumbbell, you drop it in the water and it sinks. When you go to lift the dumbbell while you're underwater, it's going to feel like it's a different weight than when it was in the air. So this new weight, how heavy it feels while it's under the water, the apparent weight, is equal to the true weight, however it actually weighs in the air, in a normal circumstance, minus the buoyant force which acts on the object because it's in the fluid. So like I said, if you have a weight, you put it in water, you go to lift it, it feels lighter in the water than it does in the air. Why? Well, because the water pushes on the object in such a way as to apply a buoyant force. That buoyant force is trying to lift, it's trying to make that object float. Now, the object, if it sinks, is too dense to float, so it'll sink. However, that doesn't mean that the water isn't trying to make it float. So it's pushing up on it to try to make it float, it's just not pushing hard enough. And that push, trying to make the object float, is called the buoyant force. So if you want to know how heavy something feels in the water, or whatever fluid we're talking about, well, first take however heavy it actually is, mass times gravity, mg, that's the weight, and then subtract off the buoyant force because it's in this fluid. Along with this, we also have some of the Archimedes principle relationships, which go like this. When you place an object into a fluid, so let's say you have a glass of water, and then you fill the water up all the way to the tip top of the glass. Then you have ice or a rock or something, and you put the rock into this glass of water. Well, what happens? The water spills over the top. This is called displacing the water. As you put this rock into the rock takes up some room, and so that pushes water out of the way, which is called displacement. And what we know is that the volume of the water displaced, like how big, the volume of the water displaced is the same as the volume of the object that you stuck into the water. Obviously, if I stick a 5-foot rock into the lake, well, that's 5 feet of lake that must move out of the way to make room for the rock. So the volume of the object will displace that amount of water. Then we also know that the buoyant force is equal to the weight of the water displaced, which this is not necessarily as intuitive, but it is nonetheless true. If we do this experiment with the glass of water filled to the very top, we put a stone into that water, some of the water will overflow. If we capture that water that overflows and weigh it, that weight of the fluid displaced will tell us the buoyant force which is being applied to the stone that moved, that displaced that fluid. And then putting this together with what we know about density, how to rewrite weight as density and things, we get that the buoyant force acting on an object is equal to the density of the object. I'm sorry, not the density of the object. What am I thinking? The density of the fluid times the volume of the object times g. And the reason we get this is because if we say weight of the fluid displaced, well, weight is mass times gravity, and mass is rho times v. Right? So if this is the fluid's density and the fluid's volume, we then use the fact that the volume of the fluid is the same as the volume of the object that was put in, and that gives us this. So this is the set of relationships, equations you can call them, which will be used for every single buoyant force / Archimedes principle question you may get. Another good one to remember, which we learned before when it came to fluids and floating versus sinking, is the density of the fluid over the density of the object is equal to, actually, you know what? Let's do it this way. This is a better way of writing it. Let's say we put something in water and we want to, and some of that object is in the water, some of it is sinking, some of it is floating. So there's a certain amount that's under the water line and a certain amount that's over. Let's say, a third of the boat is submerged in the water, but 2/3 is above the water. And we want to know what must the density of that object be. Well, we could say that the percent submerged, or the fraction of the object submerged, tells you the fraction, the density of the object over the density of the fluid. So if I say, I build a boat of a certain material, I place that boat on the water, and when I let go, it's floating, but it's floating with 3/4 of the boat under the water and 1/4 above the water. Then I can ask, what must the density of this boat be? Well, I would use this equation, I should say. Okay. So all of these have to do with sinking versus floating. This is buoyant force stuff, Archimedes principle. Very, very important relationships. With that, let's actually try a few examples. So, example 1. Let's do this exact problem, this last example I set. A boat made of an unknown material is placed in the lake. If 3/4 of the boat is submerged, what must be its density? All right. Well, this type of problem, whenever you see this fraction submerged, what's the density? You think percent submerged is the density of the object over the density of the fluid. In this case, what fluid are we talking about? We're talking about the lake, water, and I know that the density of water is 1,000. So I say, how much of my boat is submerged? 3/4 of it. So 3/4, that's the same as 0.75, 75%. 3/4 of the boat is submerged equals the density of the object, the thing I'm trying to find, over the density of the fluid, which is 1,000. So I just solved this for rho. Rho is equal to 3,000 over 4, and you get 750. And that's how this type of problem can be solved. This is very nice. You would think it's a very complicated question. What's the shape of the boat? How many windows does it have? You know, all this stuff can go into the problem, but it's actually a very, very simple question to answer. If you know how much is submerged, of course. You have to know that. But if that's given to you, then it's a very easy relationship to see what the density of this object must be. All right, let's do a different example. All right, let's say you have a metal sphere whose radius is 50 centimeters and whose density is, let's say, 5,500 kilograms per cubic meter. What is the apparent weight of the sphere if placed in water? How heavy will it feel? All right. Well, for this question, what I'd like to do is I want the apparent weight. So the equation, apparent weight, is equal to true weight minus buoyant force. So I need those two things. I need the true weight of the object, and I need the buoyant force on the objects. Well, what's the true weight? So the true weight is mass times gravity. But I'm not given the mass, I'm given the density. So I have to use the density of the object times the volume of the object. That will give me its mass, times g will give me its weight. All right, well, do I know the density of the object? Yes, 5,500. Do I know the volume of the object? Well, I know it's a sphere, and I have its radius, so I could use 4/3 pi times its radius cube in meters is 0.5 cubed. Remember, our units have to be correct. We have to use meters for distances. So 4/3 pi r cubed, that gives me the volume, then times 9.8 for g. And now I just plug this stuff into my calculator. 5,500 times 4/3 times pi times 0.5 cubed times 9.8. And I get 28221.97 newtons. So 28,000 newtons. That's how much it actually weighs. All right. What about the buoyant force? How do I calculate buoyant force? Well, if we go back to our relationships, I can use the bottom equation. Buoyant force is the density of the fluid times the volume of the object times gravity. So buoyant force is rho fluid, volume of the object times gravity. All right, what's the density of the fluid? We're in water, so it's 1,000. What's the volume of the object? Again, 4/3 pi times 0.5 cubed. And what's g? 9.8. So again, I stick all of this in my calculator and I get 5131.27 newtons. All right, so now I know how much the sphere actually weighs, and I know how hard the water pushes up on the sphere to try to make it float. So I plug these into my main equation. 28221.97 minus 5131.27. And what do I get? 23.090.6 newtons. So there we go. It weighs less than it actually weighs. You know, as it's in the water, it should feel lighter. Indeed, it does. This is a metal sphere. It's got a higher density than water, so it should sink. If I got a negative number here, that is, the buoyant force is bigger, then this thing would be floating. Of course, it's not. It's a steel ball. It sinks. So its buoyant force is less than its weight. And I just subtract the two, find the difference, and that gives me the apparent weight. So again, fairly straightforward. You put an object in a fluid, you want to know how heavy does it feel while it's under the water. Well, first, how heavy is it in reality? That's mg. And then, how much does the water push back? That's the buoyant force. Subtract those two numbers, and that's how heavy it feels to you while it's underwater. All right, let's try a third example. Let's say you have a metal sphere whose density is 3,000 kilograms per cubic meter, and whose radius is 30 centimeters. You place the sphere in an unknown fluid and measure its weight. You find that it weighs 1,500 newtons. What must be the density of the fluid? So this is nice. This is a different problem. Of course, in actuality, it's the same problem as we've done before, except we're trying to find something different. We're trying to find the density of a fluid, but what do we know? The situation is you have an object, you put it in the water, and you weigh the object while it's underwater, and you find it has a certain weight. So again, this is apparent weight is true weight minus buoyant force. Okay. This time, though, you know the apparent weight. You know that the apparent weight is 1,500. And you want to find the density of the fluid using this relationship. Well, let's do what we did before. Let's find the true weight. Let's find the buoyant force and see what happens. True weight, again, is mass times gravity for the object. We don't know the mass of the object, but we know its density, so it's rho object, volume object, that's mass, times g. So 3,000 times the volume, this is a sphere, so it's 4/3, pi times the radius, 30 centimeters, so it's 0.3 cubed, times 9.8. So we multiply all of this together, and we find that the actual weight is 3325.06 newtons. All right, that's good. So far we're okay, right? We have an object in a fluid. It really weighs 3,300 newtons. The apparent weight is less than that, 1,500. So things are making sense. What about buoyant force? Well, buoyant force is rho for the fluid, v for the object, times g. And now we see the rho for the fluid is the thing I'm trying to find. So what we want to do is take this and just plug it in for buoyant force. So here we go. True weight, 3325.06 minus buoyant force, which is rho fluid, times volume of the object, that's 4/3, pi 0.3 cubed, times g, which is 9.8. And now we have our little equation. Everything's a bunch of numbers except, of course, the rho fluid, which is the thing I want to find. So let me just erase this out of the way and I can work on it. We have, first thing I'm going to do is bring the stuff on the right, all the rho times 4/3 and all that. I'm going to bring it to the left, and then I'm going to move the 1,500 over to the right. So we have rho fluid times 4/3 pi r cubed times 9.8 equals 3325.06 minus 1,500. Okay, solve for rho. Rho fluid is 3325.06 minus 1,500 divided by 4/3 pi 0.3 cubed times 9.8. So you just want to be careful how you plug all of this into the calculator. Just do it one step at a time. You'll get 3325.06 minus 1,500. That gives me 1825.06. And the denominator, 4/3 times pi times 0.3 cubed times 9.8 is 1.108. So 1825.06 over 1.108 is 1646.6 kilograms per cubic meter. So whatever this fluid is, it's a little more dense than water. In fact, 50% more dense at 1,600 instead of 1,000. But there we go. So this question is the same as this question. Notice we're using the same equation, apparent weight equation. We try to solve for the true weight, rho vg, for the object in both cases. And we're trying to find a buoyant force. And this is where the two questions diverge a little bit. In this first example, we know everything to get a number for the buoyant force because we know the density of the fluid, we know the volume of the object. So we plug those two numbers in and we get our apparent weight. Here, however, we knew the apparent weight the whole time was 1,500, and what I was trying to do was figure out what kind of fluid we're working with, the density of the fluid. And where the density of the fluid comes into play is with the buoyant force. So here, when we do the equation for buoyant force, we can't get a number for it, so we just replace buoyant force with its equation. Rho for the fluid, volume of the object, times g. And that's when we have our equation. Apparent weight, 1,500, equals true weight, 3,300, minus rho vg. And then we just solve for the unknown, which is rho in this case. So I hope this gives you a good idea of the types of questions you're going to see for this topic. Archimedes principle, buoyant force, things like this. There are, a number of relationships, as you can see from this, box of equations sitting here, but really, they're all really related. Especially the bottom three. The top one, apparent weight, is true weight minus buoyant force. This is just an intuitive statement. When you put an object in the water, it feels lighter. Why does it feel lighter? Because the water is pushing on it, trying to help it float. And that push is called buoyant force. The bottom three in the box allow you to use that equation more efficiently. So when you put an object in a fluid, that object takes up room. So the amount of room taken up by the object is the volume of the fluid that's displaced. The buoyant force, if you want to know how hard a fluid pushes on an object to make it float, well, get that fluid that's displaced and weigh it. The weight of the fluid is the same as the buoyant force. And then finally, because this is true, there's a relationship between the object and the fluid in the buoyant force. The weight of the displaced fluid is mass times gravity for the fluid. Mass is rho times v, density times volume. But because we won't always know the volume of the fluid that was displaced, we're usually going to know the volume of the object that we stuck in there. Since they're equal, then we have our final equation. The buoyant force is the weight of the displaced fluid, which is the density of the fluid you're working with, the size of the object you put in there, its volume, times g. And then the last little relationship, which is about how much of an object is submerged in the fluid being related to its density. And in fact, the fraction submerged is the fraction, the ratio of its density to the fluid it's trying to float in. So I hope this is understandable. I hope this helps as you're trying to work these problems out yourself and work on the homework to help guide your thinking and know how to use these equations and whatnot. Best thing I could say, be careful to make sure the units you're using are correct units. Kilograms, meters, things like this. And then just be careful when you're using the density of the object versus the density of the fluid and things like that. But if you're careful, these things are a piece of cake. So, until next time.